All right, in this video, I'm going to walk through all the different problems from the first assignment from chapter 11, which is on sequences. 11.1 is on sequences, and 11.2 is on series. So the first problem in 11.1, so I guess it's 11.1, number 13, and it asks you to find a sub n formula for the sequence. And so on number 13 here, you start with the sequence 1, 1/3, 1/5, 1/7, 1/9. Okay, now there's a couple of acceptable answers. It depends how you want to number these terms. I guess you could call the first term n equals 1. You could also call n equals 0, and that'll become something that we'll do quite a bit in this section, in this chapter, for a variety of reasons. You'll see why when it gets to it. But we'll call that n equals 1, n equals 2, n equals 3, n equals 4. And this one you can eyeball, you can look at it and see it's going up by 2 each time. This first one, I guess, is 1/1. And you could look at it, it's going up by 2, so it's going to be 1/2n is the kind of slope there. And if you double the n, well, that's always 1 more, so 2n minus 1. So you could have a sub n equals 2n minus 1, where there it is. There's an explicit formula for the term numbers. All right, so that's number 13. Okay, number, let's see, 14. 14 is 1 comma negative 1/3, 1/9, negative 1/27, 1/81, and you can see that this is a geometric sequence. Each time it's multiplying by negative 1/3. So again, we can call this n equals n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. And this is 1 times negative 1/3. This is 1 times negative 1/3 squared. This is 1 times negative 1/3 cubed, etc. So here the power, the exponent on the negative 1/3 is always 1 less than the exponent. So the general formula here would be 1 times negative 1/3 to the n minus 1 equals a sub n. All right? Okay, the next problem is number 17. So 11.1, number 17. So on this one, let's see. Well, it starts out with 1/2, and then you have negative 4/3, and then 9/4, and negative 16/5, and then 25/6, ... So here it's a couple things to look at. First is, and we'll number these. This is n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. So once you number these, you can see a couple things. One is that the numerator is just n squared, and the denominator is always n plus 1. Now, if we did this, though, there'd always be positive, but if you notice, we want the ones that we want to be negative are the even ones. So what we can do is we can multiply this by negative 1, but to turn a negative into, an odd into an even, or an even into an odd, we can put it to the n. We could do it plus 1 if we want, to the n plus 1. And that way, when you plug in an even for n, the exponent then will be odd. So negative 1 to an odd will be negative 1. So it'll make the even numbered terms negative, and it'll make the odd numbered terms positive. And there we go. So this is equal to a sub n. Okay, so number 25, it asks whether this sequence will converge or not. So 25 is a sub n is equal to 3 plus 5 over n squared over n plus n squared. And this one is, you think about the limit. What's the limit as n goes to infinity of a sub n? Well, that's equal to the limit as n goes to infinity of 3 plus 5n squared over n plus n squared. And we've done a bunch of these problems, and we know that it's going to be 5. So yes, it's convergent, and it converges to 5. Okay, so number 27 is a sub n is equal to e to the 1 over n. And again, if we look at the limit as n goes to infinity of e to the 1 over n, that's going to become e to the 0, which is 1. So this is convergent, and it converges to 1. Excuse me, this sequence is convergent, and it converges to 1. Okay, so number 29, if you look at this one, as n goes to infinity, the argument of this tan, this part here, well, this 1 isn't going to matter much, and so this is going to converge to 2 pi over 8, which is pi over 4. And we know that the tangent of pi over 4 is equal to 1. So the convergence, the limit as n goes to infinity of a sub n is going to equal 1. Okay, so for 31, when you look at this one, the degree of the top is 2. It's n squared. The degree in the bottom is not as clear, but this 4n is not going to matter much. And the bottom is kind of will turn into the square root of n cubed. So this is going to be approximately equal to, as n gets big, n squared over the square root of n cubed, which is n squared over n to the 3 halves, and which is equal to n to the 1 half. So, so this is going to kind of turn into the square root of n as n gets bigger. It's going to get closer and closer to the square root of n. But as n goes to infinity, the square root of n is also going to go to infinity. So this is divergent. This is going to get really big. Another way of looking at it is just the degree of the top is bigger than the degree on the bottom. The top is clearly 2. The bottom is kind of 3 halves. Since the top is bigger than the bottom, this is just going to get really, really big as n gets big. All right, so for 33, this is going to be an alternating series. When n is an odd, the answer will be a sub n is going to be negative. When n is positive, when n is even, a sub n is going to be positive. But what's going to happen is that the top is always either going to be, the numerator is always going to be negative 1 or 1. The bottom, the denominator is always just going to get bigger and bigger and bigger and bigger. So something that is either 1 or negative 1 over some large number, and that's going to go to 0 as n goes to infinity. So this is convergent, and it converges to 0. All right, so for 35, what's going to happen here? Well, a sub n, we can look at a few terms. You're going to have, when n equals 1, you're going to have cosine of a half. And then you're going to have, for n equals 2, it'll be cosine of 2 halves, or 1. And then the cosine of 3 halves. That's supposed to be a 3. And then the cosine of 2. And this thing is always just going to be, well, it's going to be counting up. But what happens with cosine is this is in radians. Some of these will be positive, some will be negative. This thing's just kind of jumping all over the place. So there's no pi's in this thing. It's not the number inside is just getting bigger and bigger, but the cosine of a bigger and bigger number doesn't go to anything specific. So since this doesn't go to a specific number, this is a divergent sequence. All right, so for 37, this is the first time we're seeing factorials in this chapter, and I guess this year, really. But we'll be seeing quite a bit of them in the next couple weeks, so get used to them. And so factorial, keep in mind what they are. If I have something like 5 factorial, that's going to equal 5 times 4 times 3 times 2 times 1. So you multiply, you saw this in geometry. You multiply the number by each of the numbers less than it. So if you look at one like n factorial, well, that's going to be n times n minus 1 times n minus 2, down to 3 times 2 times 1. Okay, so it helps to then look at this problem and write out a few terms. If you have 2n minus 1 factorial, that's going to be 2n minus 1 times 2n minus 2, because that's 1 less than that, and then 2n minus 3, And the bottom, the denominator is going to be 2n plus 1 times, well, 1 less than 2s plus 1 is, well, just 2n. And then 2n minus 1, and then 2n minus 2, and you can kind of see where this is going. A lot of these terms are going to be the same. In fact, all the ones are going to be the same, so you're going to get canceling. Everything from then on is going to cancel. So this is going to simplify to 1 over 2n plus 1 times 2n. And if we think about the limit as n goes to infinity, well, you're going to have 1 over something that's going to get huge. So this is going to go to 0. So the limit as n goes to infinity of a sub n. So this is convergent, and this sequence is convergent, and it's convergent to 0. All right, so this problem is an interesting one. We talked about this a bit in the other class, and there's a bunch of different ways of doing this one. Gosh, there are all sorts of different ways that people had of figuring this one out. Your book, your solution manual might have one solution. Let's see, if I'm doing this one, what I'd probably do is, let's see. Well, you could rewrite it as e to the n plus 1 over e to the n over e to the 2n minus 1. And you can think about it as n gets big. As n gets large, this is going to go to 0. This is just always going to be 1. So these aren't going to matter much. So you're going to have, this is going to turn into e to the n over e to the 2n, which is equal to 1 over e to the n. And if you think about it as n goes to infinity, that's going to go to 0. So this thing's convergent, and it converges to 0. Another way of looking at it is, well, the bottom is just going to be so much larger than the top, because this thing here, since this is to the 2n, this is being squared. So e to the n is going to get large. It's squared. So something large over something large squared is going to go to 0. So you can kind of eyeball this one. There's some more formal ways of doing it. I'm sure your solution manual does a more formal way. All right, for 61, 61's basically asking, does this converge? And what you can do is you can throw this into your graphing calculator, replace n with x, and kind of see what the graph does. But you can also eyeball this one. You can kind of look at it and say, okay, well, as n goes to infinity, this stuff is going to become more or less 1. So this is going to be very similar to 1 times cosine of n. And cosine of n, just like we saw earlier, you can get cosine of 1, cosine of 2, cosine of 3, cosine of 4. That's going to be sometimes positive, sometimes negative. It's going to kind of be bouncing up and down and bouncing from place to place. It doesn't converge on anything. So this is definitely a divergent series. And you'll see that if you look at the graph of this thing, it's just going to kind of go up and down, and it doesn't, if you've replaced n with x and looked at it, it's all over the place. It does not converge to a single number. All right, 79 is one of my favorites, and I might have to actually save this one for class. There's a couple different ways of looking at it. I'm curious how you guys think about it. And yeah, there are a couple different ways of looking at it. So I'm gonna kind of not do this one right now. But one way, well, no, I won't say anything. I'll let you guys think about this one. All right, so 13, I told you to ignore the instructions. Oh, this is an 11.2. So 11.2, number 13. I said ignore the instructions and just start writing out the series. And if you start writing this one out, the sum of this, well, if you plug in n equals 1, you get 1 over 1 minus 1 over the square root of 2. And you plug in n equals 2, and you get 1 over root 2 minus 1 over square root of 3. You plug in 3, and you get 1 over root 3 minus 1 over root 4. Plus, and if you were to, let's say you added up the first n terms, you can see the canceling going on here. Let's say you added up the first k terms. Well, you'll start with a 1, but then you're going to end up with a 1 over the square root of k plus 1. And if you think of this, and so we've added up the first k terms. So this is the partial sum, the first k terms. And if we look at the limit as k goes to infinity, this is going to equal 1. So the sum of this series, this is a telescoping series, the sum of this series is 1. It is convergent. Okay, so number 15 is asking to look at this. The sequence and the series given here. And if we look at the sequence, well, as n goes to infinity, the limit as n goes to infinity, so part A is saying, let's just look at the sequence of a sub n. If we look at the sequence, well, these terms are going to approach 2/3. So the sequence is convergent. The sequence converges to 2/3. But if we think about, on part B, the sum from n equals 1 to infinity of a sub n. Well, eventually, since these terms are going to go to 2/3, eventually you'll be essentially just adding 2/3 plus 2/3 plus 2/3 plus 2/3, or something very close to 2/3. And it doesn't take too much imagination to see that that is going to go off to infinity, that this is a divergent series. Series is divergent, the sequence is convergent. All right, so this series, well, one thing people in the other class missed, that it told you that this was geometric. And so that's key, is that it is geometric. You can see, even if you weren't told it's geometric, you can see that from here to here, what happened? Well, it divided by -5, and then divided by -5 again is 2 divided by -5 is 2/5, which is 0.4. You divide 0.4 by -5, and you get -0.08. So what's happening, you're either dividing by -5, which is the same thing as multiplying by -1/5. So the key thing here with a geometric series is identifying the first term. The first term is 10, and identifying the multiplier, which is -1/5. So the sum of this series, the sum of any infinite series where the absolute value of r is less than 1, is going to be the first term over 1 minus the multiplier. So in this case, it's going to be 10 over 1 minus -1/5, which is going to be, well, I do a little math, 10 over 6/5, which is going to be 50 over 6, which is 25 over 3. So there is your sum of that infinite series, that infinite geometric series. It's a convergent geometric series. Okay, so number 20 has 2 plus, and then 0.5 plus 0.125. Well, this is 2, this is plus a half, this is plus an eighth. Well, the next one I'm going to guess is 1/32, because what's happening each time? Well, each time we're multiplying by 1/4. So the first term is 2, the multiplier r is 1/4, and since r is less than, the absolute value of 1/4 is less than 1, this is convergent, and the sum of this infinite series is going to be the first term, 2 over 1 minus the multiplier, 1/4. So this is 2 over 3/4, which is equal to 8/3. So 8/3 is the sum of that geometric series, that convergent geometric series. Okay, so 43, well, it's in the section where they're talking about telescoping sums, because if you just were to start to do it, and you looked at a few terms, well, when n equals 2, you'll get 2 over 3. When n equals 3, you'll get 2 over 8. When n equals 4, you'll get 2 over 15, and right now, when n equals 5, 2 over 24, you're not going to notice anything special in this problem. However, if you do a little partial fractions with this, 2 over n squared minus 1, well, equal to a over n minus 1 plus b over n, and you solve for a and b by clearing fractions, you'll find that 2 over n squared minus 1 is equal to 1 over n minus 1, and then minus 1 over n. And that is very, very helpful, because now if I start writing out a few terms of this series, when n equals 2, I'll get 1 over 1 minus 1 over 2. When n equals 3, I'll get 1 over 2 minus 1 over 3. n equals 3, I'll get 4. I'll get 1/4 minus 1/3. And so if I go up to the kth term, what I'll end up with is 1 over, and then minus k. And as k goes to infinity, you can see this is going to converge to 1. This part here is going to go to 0. So this goes to 0. So this whole series will go to 1. It's convergent to 1. All right. So this one, if I start writing out a few terms of this, I'll have the natural log of a half plus the natural log of 2/3 plus the natural log of 3/4, and it keeps going that way. And it's not really clear what's going on here, other than these terms, the argument on each one of these, this is kind of interesting, the argument of each of these is getting closer and closer to 1. Of 1/2, 2/3, 3/4, 4/5, 5, 6, eventually 99 100ths. Well, if the argument's going to 1, that means that the natural log of that is going to 0. So the question is it going to 0 fast enough? Well, this one gets really interesting, and I can telescope this really easily. I don't need partial fractions, because what I can do, just using a property of logs, I can say that this is equal to the natural log of n minus the natural log of n plus 1. And if I start looking at a few terms, well, I plug in 1, I will have, I'll have the natural log of 1, minus the natural log of 2. I plug in 2, I'm going to have the natural log of 2 minus the natural log of 3 plus the natural log of 3 minus the natural log of 4. And so the question is, does this converge? Well, if I looked at the first k terms, well, all this stuff will cancel out, except I'll have this natural log of 1 in the beginning, but I'm going to have minus the natural log of k plus 1. If I look at the first k terms. And if I look at then the limit as k goes to infinity, hope you can read what I'm writing here, k goes to infinity, well, natural log of 1 is 0, but then you're going to have minus the natural log of something that's going to infinity. And that natural log of a really big number is, doesn't grow that quickly, but it is going to go to infinity. So you're going to have, this is going to end up being negative infinity. So this is a divergent series. Divergent. So we can telescope it to realize that these terms are going to 0, but they're not going to 0 quick enough. This thing is going to just add up, and eventually just get too big. Actually, too negative. So I guess you could say that's too small. Okay, and last but not least is 47. And 47, it just helps to write out a few terms. So 47 is the sum from n equals 1 to infinity of e to the 1 over n minus e to the 1 over n plus 1. And if you write out a few terms of this, you plug in n equals 1, and you'll have e to the first minus e to the half. There's n equals 1. Plus n equals 2, you're going to have e to the 1/2 minus e to the 1/3. And then plus, and you'll have e to the 1/3 minus e to the 1/4. And plus, let's say if we did the first k terms of this, well, all these would cancel out, except I'd have the e to the 1 from the beginning, and I'd have minus e, and if I did the first k terms, I'd have 1 over k plus 1. So this is the sum of the first k terms. So we could call it s sub k. And as k goes to infinity, well, this exponent here is going to go to 0, which means e to the 0 is going to be 1. So this is going to go to, as n goes to infinity, the sum of this is going to become e minus 1. So it is a convergent series, and it converges to e minus 1.